Have you ever looked at a massive steel ship, something that weighs thousands of tons, and just wondered, how on earth does that not sink? Well, today we're going to pull back the curtain on the invisible force that makes it all possible. And trust me, by the end of this, you'll see the world around you just a little bit differently.
It's one of those classic questions, right? One of the first things we wonder about as kids. You toss a stick into a pond, and it bobs right on the surface. You throw a rock, and plunk, straight to the bottom. But what's really going on there? What's the secret?
And you know, the more you think about it, the weirder it gets. A light, air-filled beach ball? Okay, floating makes sense. But then you have a gigantic iceberg weighing millions of tons, and it floats too. Meanwhile, a tiny little pebble sinks without a second thought, so it's definitely not as simple as just weight or size. There's something else at play. And check this out. It's not just a simple yes or no question of floating. Notice how a beach ball bobs along with almost all of it sitting above the water. But that massive iceberg, it hides nearly 90% of its gigantic self under the surface. So what in the world determines how high or low something floats? Okay, we've got a real mystery on our hands. All right, let's start solving this thing. To get to the bottom of it, we need to look at our first major clue, which is all about what happens the very instant an object is placed in a fluid, like water.
So imagine you push a little cube under the water. The water doesn't just sit there. It immediately starts pushing back on that cube from every single direction, from the top, the bottom, and all four sides. It's completely surrounded. This constant push is what we call pressure.
And right here, this is the absolute key to the entire puzzle. That pressure, that push from the water, isn't the same everywhere. The deeper you go, the more water is piled up on top of you, and the stronger that push becomes. This one little fact is going to unlock everything for us. So let's go back to our cube for a second. The push on the left side is perfectly matched by the push on the right side. They're in a standoff. They just cancel each other out. But what about the top and the bottom? Well, since the bottom of the cube is deeper in the water than the top, the water is pushing up on the bottom with more force than it's pushing down on the top. So you see what's happening? When you add it all up, that imbalance creates a net force that is pushing the object upwards. And this invisible upward lift has a very cool name, the buoyant force. This is the hidden force that's constantly trying to make things float. Okay, great. So we found our culprit, this upward buoyant force. But that just opens up the next big question. I mean, how strong is it? How could you possibly calculate this invisible push, especially on something with a complicated shape, like a weirdly shaped rock or a boat? Well, for the answer to that, we need to travel way back in time to ancient Greece for a truly brilliant thought experiment from a guy named Archimedes. It's pure genius.
Now here's the core insight, and it's a big one. The buoyant force is just the water pushing back. And the water doesn't care what the object is made of. All it cares about is the space the object is taking up, its shape and volume. So the buoyant force on a rock would be exactly the same as the force on a piece of styrofoam of the exact same size and shape. The material is irrelevant.
Okay, so follow this incredible piece of logic. Stick with me here. 1, we know there's an upward buoyant force on our submerged object. 2, imagine you could magically swap out that object with a blob of water of the exact same shape. The buoyant force on that water blob has to be the same, right? Now here's the aha moment. We know that blob of water isn't going anywhere. It's just sitting there, perfectly happy. It's not sinking or rising. For that to be true, the upward buoyant force must be perfectly balancing the downward weight of that blob of water. And boom, there it is! And that right there is Archimedes' Principle. The upward push an object feels is exactly equal to the weight of the water it pushes out of the way. It's just so incredibly simple and elegant once you see it. So now we have everything we need. We've identified the upward force, and thanks to Archimedes, we know exactly how to measure its strength. We can finally solve our original mystery once and for all.
You can think of it like a cosmic tug-of-war. You've got gravity pulling the object down, that's its weight, and you have the fluid pushing it up. That's the buoyant force. If the downward pull of weight is stronger, the object sinks. If the upward push of buoyancy is stronger, it floats. It's as simple as that.
But hold on, we can actually make this even easier. Remember, Archimedes told us the buoyant force is simply the weight of the fluid that gets pushed aside. So the battle is really between the object's own weight and the weight of an equal volume of the fluid. And that whole comparison boils down to one beautiful, simple concept: density. Density is just how much stuff is packed into a certain amount of space.
If an object is more dense than the fluid it's in, it sinks. If it's less dense, it floats. That's it. That's the entire secret.
So now that we have this master key, this simple rule of density, let's go back and unlock some of those real-world puzzles we started with.
Let's look at that iceberg. The density of ice is about 920 kilograms per cubic meter. Seawater is a bit denser, around 1,000. Because their densities are so close, the iceberg has to push a huge amount of water out of the way just to create enough buoyant force to offset its own massive weight. And that's exactly why you only see the tip of the iceberg.
But what happens in that really special case, where the object's density is exactly the same as the fluid's? Well then, the forces are perfectly balanced. The object won't sink, but it won't rise to the surface either. It just hangs there, suspended. We call this neutral buoyancy, and it's the trick behind how submarines can hover in the deep.
A submarine is basically a master of density control. To dive, it opens up big tanks and floods them with seawater. This makes its overall average density go up, and it sinks. To come back up, it uses powerful compressed air to blow all that water out, making it less dense so it rises. And to just hover, it fine-tunes the mix of air and water to perfectly match the density of the sea around it. Pretty cool, huh?
And get this same exact principle is used for something literally out of this world. NASA has a gigantic swimming pool called the Neutral Buoyancy Lab. They put astronauts in their big, bulky spacesuits and adjust their weight until they are perfectly neutrally buoyant. This lets them float effortlessly in the water, which is the closest thing we have on Earth to simulating the weightlessness of space.
So there you have it. From a simple thought experiment in ancient Greece all the way to training modern astronauts for spacewalks, this hidden upward force is absolutely everywhere. It just goes to show you that sometimes the most amazing secrets are hiding in the simplest questions. It makes you wonder, what other invisible forces are out there, shaping our world in ways we've never even noticed?